Okay, get this. Imagine creating, like, stunning photorealistic pictures and with AI in just 2 steps.
Wow.
Yeah. It's not sci-fi, right? It's the potential of what are called consistency models, and that's exactly what we're diving into today. And you sent over some fascinating research on this, focusing on the continuous time approach.
Yeah.
From what I'm seeing, it's been a challenge for researchers, but man, the payoff could be huge.
It really could. Whether, you're someone who's deep into AI or just curious about how art is evolving, I think understanding this research is like it's like getting a sneak peek into the future of image creation. Plus, we're gonna uncover some really surprising facts about how these AI systems actually work, how they do their
I
thing.
love it. I love it. Okay, so first, just a little context. We all know that the current AI image generators, the ones that are out there, things like diffusion models, they can make, just incredible pictures, but they're slow.
Yeah, they're notoriously slow.
They're super slow, and I'm guessing that has something to do with how they actually create the images.
You're exactly right. It's all about the process, right? So imagine you take a pristine image and you just start adding noise to it bit by bit until it becomes just pure static, just
The
completely.
key V static.
Exactly. That's
Yeah.
what these diffusion models are doing. And then they train an AI to reverse that process, to painstakingly remove the noise step by step until you get back to that original image.
So each step brings the image closer to clarity, but it takes forever to get there.
Yeah. Yeah, it's kind of like meticulously trying to reconstruct like a shattered vase.
Ooh, that's a good analogy.
Yeah, but there's a potentially better way. And that's where these consistency models or CMs come in. So instead of this slow step-by-step denoising, they basically try to map a noisy image directly to a clean one, potentially in one step.
Wow. That's a huge difference. So instead of like going piece by piece, they see the whole picture at once.
You got it. You got it. But there are two main types of these CMs. There's what's called discrete time and there's continuous time. So think of like a timeline, right?
Okay.
Representing the image's journey from noise to clarity. So these discrete time CMs, they're kind of like taking snapshots at specific points along that timeline.
Okay.
Whereas continuous time is like having this like smooth, unbroken video recording of the entire process.
Oh, okay. So in theory, continuous time should be more accurate, right? Like having a higher resolution video.
You would think so. You would think so. But training them has been like a real challenge, right?
Yeah.
It's kind of like think of it like trying to balance on a tightrope. One wrong move and the whole thing falls apart.
Okay.
And that's where this research from OpenAI becomes so exciting.
Yeah. So from what I've read, they've kind of managed to do what was thought to be impossible, which is they've actually stabilized and scaled these continuous time CMs.
Hmm.
They call their model SCM, and it's achieving some pretty incredible results.
And the secret sauce is this new formulation they call trig flow.
Okay.
So imagine like a new language that's specifically designed to like describe how these AI images change over time.
Okay, so they've basically created a whole new way of speaking AI.
Yeah, that's essentially what they've done.
Yeah.
Yeah, they made the process much smoother and easier to kind of control.
Gotcha. But how did they solve that instability problem? I mean, what were the specific steps they took to make these models actually work?
Well, they had a multi-pronged approach, right? They tackled the problem from different angles.
Yeah.
So, for example, they figured out a way to like prevent this common issue where the model would essentially just kind of blow up
Yeah.
near the end of the image generation process.
Oh, wow.
They also refined how the model understands time, right? So it's
Mm.
it's less like a choppy radio signal and more like like crystal clear digital audio.
Yeah.
So
It sounds like they went really deep into like the mechanics of these models to really fine-tune things. But did it actually work? I mean, did they actually manage to make these continuous time CMs a reality?
they absolutely did.
Yeah.
They trained SCM on some of the toughest data sets out there, like
Mhm.
like Sci-Far 10 and ImageNet.
Yeah.
They even trained a massive model with 1.5 billion parameters
Oh.
on ImageNet 512 by 512.
Wow.
That's huge EE.
Okay, I'm no AI expert, but even I know that bigger models usually mean more complexity, slower training.
Right.
So how did they manage to train something that massive?
That's where their ingenuity really shines through. They found ways to make the training process much more memory efficient.
Ugh.
It's like It's like they figured out how to pack a suitcase for a month-long trip using only a backpack.
That's a good analogy.
Yeah.
Yeah, I like that. So more efficient training. But what about the results? Did all this effort actually lead to better images?
The results are really impressive. So they used something called FID scores,
Oh,
which essentially measure how realistic and high quality the generated images are.
gotcha.
And get this, SCM achieved FID scores comparable to like the state-of-the-art diffusion models,
Wow.
but in just 2 steps.
Wow.
Remember, diffusion models often need like dozens or even hundreds of steps
Right.
to achieve similar results.
Hold on. Are you saying that this new model is not only faster, but it's also just as good as the current like top performers out there?
Yeah.
That's a game changer.
It really is, and there's evidence that this is just the beginning, right?
Yeah.
So their research also included what's called a scaling study,
Yeah.
showing that SCMs could potentially become even better with more computing power.
So the more powerful the computers get, the better these images will become.
Exactly.
Yeah.
But it's not just about speed and quality.
Okay.
Remember that other fast method we talked about,
Yeah.
variational score distillation, or VSD.
Yeah.
Well, SCMs have another advantage. They're better at producing diverse images.
You mean they don't create those kind of creepy same face images that sometimes plague AI art?
Exactly.
Yeah. Yeah. Why is that? What's the difference?
It all comes down to how they learn, right?
Yeah.
So VSD, it focuses on capturing like the average characteristics of
Okay.
a data set.
Yeah.
So if you trained it on faces, it would learn like an average face, and that's what it would spit out over and over again.
So it's like creating a portrait by blending 100 different faces together. You end up with something that looks vaguely human, but not quite right.
You nailed it. SEMs, on the other hand, they preserve more of the individual variations within the data set. It's like capturing the unique features of each face in the portrait,
Gotcha.
resulting in a more diverse and interesting collection of images.
That makes sense. So SEMs are faster, potentially even higher quality, and they avoid that same face problem that we see a lot. But what does this all mean for someone who's not an AI researcher? Why should our listener care about this?
Imagine a world where you can generate any image that you can think of almost instantly.
Yeah.
This research suggests that future is closer than we think.
Yeah.
And it's not just about art, right?
Yeah.
This could revolutionize everything from design and advertising to scientific visualization and even medical imaging.
That's amazing. We could see an explosion of new art forms, innovative designs, even like personalized visual experiences.
Exactly. But there's one more thing that I find particularly fascinating. The researchers mentioned that SCMs could potentially be trained without relying on pre-trained diffusion models.
Wait, are you saying that in the future, anyone with a computer might be able to create AI art without needing access to these huge, expensive models? How is that even possible?
It's a concept they call consistency training,
Okay,
as opposed to consistency distillation,
gotcha.
right? So right now, training those massive diffusion models, it's like trying to bake a cake
Okay.
with industrial-sized ovens and tons of ingredients.
Yeah.
It's a resource-intensive process.
Right.
That's only accessible to a few.
But with consistency training, it's like baking that same cake in your own kitchen with everyday ingredients.
Exactly.
That's pretty revolutionary.
It is, and that raises some really interesting questions, right?
Yeah.
What if this consistency training approach becomes even more powerful
Yeah.
than using existing models as a starting point?
Wow.
What could that mean for the accessibility and development of AI image generation tools?
It seems like we're on the verge of like a paradigm shift.
Yeah.
But before we get too carried away, we've talked a lot about the benefits of SEMs, but how did OpenAI actually make these improvements? What were those like specific tweaks that they made to stabilize the models?
Well, it's amazing, how they managed to like make such a complex topic and almost seem simple.
It really is.
Yeah.
It's a
That's a key takeaway, I think, from this research. The power of simplicity.
yeah.
They didn't overcomplicate things.
Yeah.
And that really, really paid off in terms of stability and scalability.
Can you give me an example? Like how does simplicity lead to better results in this case?
Well, think of it like like building a house,
Okay.
right?
Yeah.
If the foundation is strong and straightforward, you can build a taller, more elaborate structure without worrying about it collapsing, right?
Yeah. Yeah.
The same applies to AI models.
Yeah.
Right. By simplifying the underlying math and architecture, they essentially made the model more robust
Gotcha.
and reliable.
So it's less likely to like blow up during training, like you mentioned earlier.
Exactly. And this robustness is crucial for scaling these models,
Hmm.
to handle more complex data sets, generate higher resolution images.
Hmm.
It's like, building a bridge, right?
Yeah.
A simple, solid design can support much more weight
Right.
than a complex, flimsy one.
Makes sense. We talked about the potential for SCMs to be trained from scratch, but could this research also improve the way we train those massive diffusion models that are kind of the industry standard right now?
That's a great question, and the answer is a resounding yes.
Okay.
The techniques they use to stabilize and scale SCMs could potentially be adapted and applied to diffusion models as well.
Oh, wow.
Imagine being able to train a state-of-the-art diffusion model on a personal computer
Yeah.
instead of needing like a massive server farm.
Wow, that would completely change the game. It would open up a whole new world of possibilities for artists, designers, researchers who, don't have access to those kinds of
It
resources.
would be a huge step towards, what they call democratizing AI image generation.
Right.
Right. Allowing anyone with a good idea and a decent computer to contribute to the field.
This research feels like a turning point, like fundamental shift in how we think about AI image generation.
Yeah.
It's incredible to think about the possibilities.
I agree. This research has laid the foundation for a new era of AI-powered creativity.
Yeah.
And I'm excited to see what emerges from it.
We've learned so much in this deep dive, but it feels like we've only scratched the surface. I'm already thinking about the next layer of questions this research raises.
And that's the beauty of groundbreaking research, right?
Yeah.
It not only provides answers, but it also sparks new questions, pushing the boundaries of what we thought possible.
Absolutely. Well, to our listeners, thank you for joining us on this journey of discovery. We hope you've gained a deeper understanding of the exciting world of AI image generation. Until next time, keep exploring, keep questioning, and keep imagining the future.